electrical engineering. Again, we move into the second module, and in the second module, we discuss hardcore electrical engineering, that is the machines, the electrical machines. The machines have a lot of the machines can be understood very nicely if we follow what we have been doing in the first module, that is the circuit approach. There is also a signals and systems approach which will be dealt with later on. However, the machines, the problems associated with machines in gate examinations need to be addressed by a kind of a visualization that you need to have as you try to read through the problem. However, the questions from gate examinations have been divided into different sections, as was mentioned earlier. And here we'll be looking at both two parts of DC machines. Okay, of course, generators and motors are combined together, but there are different aspects that we'll be trying to differentiate and learn. Then again, transformers, both single phase and also three phases transformers in two sections. Induction machines, both especially motors, and then of course single phase induction motors, other generalized motors, etc., and generators and synchronous machines. Okay, again motors and generators. Okay, so in this manner, we have 8 sections. Okay, and in the first section we go on to what may be called as the preliminaries of DC machines. Okay, and in DC machines, in this session we are going to discuss some of the basics, which include both speed and EMF. Okay, later on we'll be looking at speed control, which has more to do with motors. We'll also have a look at the torque relations. Of course, it has everything to do with motors, and then we'll be looking at loss efficiency, etc. Again, DC machines. Okay, so let's have a brief view of the different formulae that you will be using. Okay, in fact, they are the only formulae that we are going to use. But then how to use them and which one to use, etc., has to be done judiciously, and this is where I think I can try to help. So this formula for the generated voltage when you are considering a generator, or for the back EMF, which is actually a reaction of the motor with respect to whatever it is doing, or when the power supply is applied to it, wherein the conversion is happening. So in both these aspects, in both these, the voltage that is developed in the armature remains the same. Okay, so it's very important, and it is one of the most important equations that we are applying, and which we are applying even subconsciously, and it's going to be very important. Okay, so we are having EG, which is the same as equal to EB. When you are considering a motor, it's given by 5 per pole, because each of these poles is responsible for creating the voltage. Okay, Z in each of these conductors. Okay, not just turns. Okay, in each of these conductors, an EMF appears as per Faraday's law of electromagnetic induction. N, every rotation counts. Okay, and P, and again every pole is now responsible for creating a voltage. Okay, that's the meaning of this formula. And of course, then the voltages are coupled together in different or divided into different circuits, and so we are having on the denominator A, because A tells us the number of paths that are available. Okay, so for lap wound winding, I hope you realize that A is equal to P, and for wave wound it's equal to 2. Okay, and of course everything is associated with respect to second. That's the reason why there's a 60 also on the denominator. So all through you must remember 5Zn by 60 into P by A as the EMF generated in a generator, or in the back EMF created in a motor. Okay, another important equation happens to be with respect to a motor wherein a power is developed. Okay, and the power is developed as given as equal to EB into IA. Okay, when you're talking about a generator, the voltage that is given outside, that is V into I. Okay, the current is going to give us the power developed. In this case, there's a power developed which can be seen only as a motoring action. So it is the same as it can be now equated to what is created by the motor, that is equal to EB into IA. Okay, that's equal to 2 pi nt by 60. Okay, so this is another important formula that we'll be using over and over again. Okay, and then we also need to know that the voltage relations. Okay, the third set of equations that we need to remember happens to be that for a generator, if EG is created, then there is a drop across the resistance, the armature resistance, and the rest is made available. Okay, so it's equal to Eg minus IARA, which is equal to the available voltage for the outside. Okay, on the other hand, voltage V is impressed, from which IARA is removed, and the rest becomes what is called as EB. Okay, of course there is a drop for in the series motor also. So of course we have to remember that the shunt winding is there and the series winding is there. The series winding also takes in a drop, and only the rest goes into the motor, okay, or the generator. Okay, so the rest is available for the at the terminals for the generator. Okay, and of course we also need to remember that there are torque speed equations for the motor, wherein for a series machine the torque is given by Ia square, because torque is always equal to phi Ia. Okay, so for a series motor, because the flux and the armature current actually produces the flux, so it's proportional to Ia square. Okay, for a shunt machine it's going to be phi Ia. Okay, for shunt motor. Okay, and the speed torque relationship is reciprocal, is like a hyperbola for the series motor. On the other hand, we are having a drooping characteristic. Okay, so these are some of the things that we had better remember as we try to do the problems. Okay, so in addition to this general construction where we have that armature, the brushes, and then the field, perhaps it's shunted or it's a series, or you may have a compound where we have long shunt, short shunt, etc. All those possibilities are there. So this is the general scheme that we have for a DC machine, be it a generator or a motor. But there are other windings as well, and there are other phenomena as well. Like for instance, we have commutation problems, so used interpoles. Okay, and then you also have what are called as armature reaction. Armature reaction, again we have having cross magnetization, as also aiding, as also opposing magnetization, etc. These are hindrances at times. Okay, and sometimes they are actually the manifestation that something is happening. Okay, so all these aspects are there, and so compensating windings are used for neutralizing the armature reaction, and the interpoles are used for improving commutation. Commutation is when the brush goes from one commutator to another, okay, without much sparking. Okay, so that is the first question. And in the second question, again some applications are coming to the picture. So let's, as we read, I hope you have a piece of paper and a pen, even in the GATE examination context, and what you get you write down immediately and put them into some of the equations that we have learned, and then do it appropriately. Okay, so 8 pole, so immediately 8 DC generator. So it's a generator, remember, has a simplex waveform. So A is equal to 2, containing 32 coils. Okay, 32, how many turns are there? 6 turns are there. So 32 into 6 into 2, that gives you the conductor Z. Okay, because 32 coils means each of these coils has 6 turns, and each of these turns have 2 conductors. Okay, so its flux per pole is 0.06 Weber. So it has to be described in Webers. Okay, the machine is running at 250 RPM. So N is equal to 250. So phi is 0.06, Z is 32 into 6 into 2, N is 250. Phi Z N by 60 is there. P is number of poles 8, and waveform, so on the denominator 2. As simple as that. And so you see that from the options you can have a rough estimate. That's enough, because the answers are differing by large numbers. So you can immediately go for the answer C. Okay, so this is where the approximations are going to be very much useful. Okay, especially when you're looking at DC machines. Okay, so this was where we applied the most important equation, which does not occur often. Okay, so the next problem we'll see is a little different, where we'll be using either V minus IARA is equal to EB, or EG plus EG minus IARA is equal to V. Okay, so that may be one of. Okay, and of course the fact that the voltage is now that is voltage generated, it could be as a back EMF, it could be as a generator EMF. They are all proportional to the speed. Okay, they are also proportional. Phi Z N, so phi and N. Okay, the Z is fixed, the others are all fixed. So it is EB is also going to be proportional. EB and EG are going to be proportional to phi and N. Okay, so let's see what we have. Separately excited. Immediately remember that the shunt field is missing. It is separately excited. So phi is going to be constant. Okay, 150 ampere separately excited DC generator supplies 150 amps to a 145 volt grid. So at the terminals you are having 145 and it's supplying 150 amps there. Okay, or in other words, the generator is supplying much more than 150 amps. It also has to supply perhaps something else. Okay, let's see what it is. The generator is running at 800 rpm. So N1 is equal to 800 rpm. The armature resistance of the generator is 0.1. So we are having a drop. Okay, so the drop is created out of 150 amps flowing through the 0.1. Okay, and creating a 15 volt drop there. Okay, so or in other words, now we can see that Eg is equal to 145 plus 15. So immediately you can start doing, though the methodology is written out there. Okay, the speed of the generator is increased to 1000 rpm. Okay, so now suddenly we are changing the speed from 800 to rpm. Okay, the current in amperes supplied by the generator to DC grid. Of course, it supplies more current. That's the reason why we are running it at a faster rate. Okay, so these are some. So increasing the input. What are the two inputs that you can increase? The flux or the speed. Okay, so in this case we are increasing the speed. So what do we have here? We have Ia1 is equal to 150, Eg1 is equal to 145 plus 150 into 0.1, which was discussed earlier, which is equal to 160 volt, and this is proportional to both N1 and Phi1. We earlier said that this is a separately excited machine, so Phi1 remains constant. It's Phi1 and Phi2 are the same. Okay, that is for 800 rpm as also for 1000 rpm they remain the same. So next is going to be Eg2, which is given by again. Yeah, so we have 160 is proportional to 800. Okay, so what do we have as Eg2? Eg2 is now going to be that is, if 160 is proportional to 800, then what is Eg2 when we have 1000 rpm? Okay, as the speed. Okay, so it's obviously that cross multiply you get 200 volt. Okay, and so what is Ia2? Ia2 is the same as equal to 200 is made by the generator. 145 is the standing voltage or the voltage of the grid. So 200 minus 145 divided by the resistance in between, which is armature resistance, which is equal to 5. So you get which is equal to 0.1. So you get that's equal to 550 amps. Okay. Again, you can do it very quickly, but in these cases, you had better be a little careful about the computation because it will give you, it won't give you negative marks, but only very little deviation from the answer is tolerated at the gate examination level. Okay. So let's move to the fourth problem. A DC shunt motor is running at 1200 rpm when excited with 220 volt DC. So 220 volt is proportional to 1200 rpm, and of course, unless of course there's a drop in the armature. Okay, neglecting the losses and saturation. So everything is neglected, which means that the flux is considered to be constant. Why? Because it's a shunt motor. Okay, the speed of the motor when connected to 175 volt DC. So what has happened is that you change the power source to another source which has only 175 volt. So what happens? The speed definitely, because the voltage has decreased, the speed definitely decreases. So we have 1050 is rolled out, 1200 is rolled out, and 750 and 900 matter. Okay, but then the reduction is so very small such that the speed can't go down as much as 750 rpm. Okay, so you can always calculate as 1200 divided by 220 multiplied by 175, which will come to near around 940 or something like that. But you can choose in this case, okay, because you are having some losses. Okay, moving on to the fifth problem. Okay, it's a long problem, so as we read, we make comments. Okay, a 250 volt DC shunt motor has an armature resistance of 0.2, okay, and a field resistance of 100. So immediately what do you see? 2.5 amps is drawn by the armature, by the field. Okay, because 250 volt is given and there's a shunt field of resistance 100 ohms. So 2.5 goes away to the field. Okay, when the motor is operated on no load at rated voltage, so there's no load, but the rated voltage of 250 is given, it draws an armature current of 5 ampere. Okay, so we are seeing that out of 5 ampere, so it's armature, so it's drawing a current of that armature current is creating a drop which is given by 5 into 0.2, that is equal to 1 volt. Okay, and runs at 1200 rpm. Okay, so now we are having a case wherein no load running is happening, and that's at 1200 and it takes 5 amps. Okay, when a load is coupled to the motor, it draws total line current of 50 amps. Okay, so 50 into 0.1 is going to be the drop in the next case. Okay, with a 5% reduction in the air gap flux. Okay, so we are reducing the flux also. So the input is getting reduced. Okay, so there are two things happening together. We have made the machine run at a higher speed. Okay, and at the same time we have Yeah, so we we have also reduced the flux. Okay, voltage drop across the brushes can be taken as 1 volt per brush under all operating conditions. Okay, now we are asking for the speed. The speed of the motor in RPM under this loaded condition is closest to. Okay, so one of the 4 answers are there. Okay, so here in this case, I can tell you that you can go for 1220 directly. Okay, why? Because it is running at 1200. Okay, you have reduced the flux. This is the major method for increasing the speed. Reduce the flux, you get a higher. Okay, and I have also calculated on the side to convince you that when you're seeing a 5% reduction in the flux, remember that you're going to have a higher speed. Okay, so you're going to have a much higher speed, which actually tries to contend with what is happening with respect to the voltage. Okay, so we are having 250, that is the original voltage, minus 1 the voltage across the armature resistance, minus 2 the 2 brushes, 1 volt per brush, there will be 2 brushes, so we are having what is called as 247 volts. This is proportional to 1200 into 5. Okay, so so flux we call it as simply 5 now. In the second case, when we are having a reduction of flux, it is 250 minus 50 amps into and the 50 amps, take out 5 amps. Okay, so take out 250 divided by 2.5 amps, so 45 amps, 45 into power, so 45 into the point to resistor. Okay, and then we also have minus 2 volts. Okay, so we see that the voltage has now reduced to 237.5. So reduction of voltage would tell us that the speed also reduces. But on the other hand, what has happened is that the flux is reduced dramatically. It has come down to 0.955. Okay, so of course when you look into the expression of N is equal to 1200 into 237.25 divided by 247 into 0.95, we can see that there is 247 into 0.95. I'm just elaborating on this point. 247 into 0.95 means that there is a reduction of 0.05. Okay, so 0.05 means divided by 20. So around only there is a reduction of around 20, that is more than 12. Okay, so more than 12 volts from 247, that is a little less than 237. So definitely on the denominator we are going to get the lesser quantity, so the speed has to increase, and that's equal to 1220. You can do it in a regular manner also, and you can get 1000. Okay, regress manner also you can get what is called as 1220 RPM. Okay, this is just for improving your concepts. Okay, so moving on to the next problem, sixth one. Belt driven DC shunt generator. Okay, of course the belt is required because the generator has to be coupled to a motor such that it can give the prime mover, it can give the motive power to the generator. Okay, running at 300 rpm. So the prime mover is running it at 300 rpm, and it delivers 100 kilowatt to a 200 volt grid. So how much does it deliver? It delivers a current of 100 kilowatt into 1000 divided by, to make it watts, divided by 200, so many amps. Okay, it continues to, okay, now what has happened is that the belt breaks. It continues to run as a motor. Why does it run as a motor? Because it has already got what is called as a moment of inertia. So now it is, so it is now running as a motor. Okay, now because of the EMF inside. What is that EMF? Back EMF. Okay, so now it becomes a motor because of the EMF inside. Okay, and taking 10 kilowatt from the DC grid. Okay, so it takes 10 kilowatt from the DC grid. Okay, and the armature resistance is, okay, so we have a change of scenario. Earlier it was a generator, it was delivering 100 kilowatt and 200 volt DC from the same grid. Now it takes only 10 kilowatt because it's running as a motor, because the belt has broken. Okay, the armature, so the armature resistance is 0.025 ohms. Field resistance is 50 ohms. Immediately as you encounter the field resistance, divide the available voltage by 50 and remove that particular current. Okay, so we are having 200 by 50, 4 amps. Okay, so 4 amps is going to be applicable for both the motor and the generator because that is steady. Okay, that is 200 volt applied across the shunt field. Okay, and the brush drop is 2 volt. Okay, so that's also steady. Ignoring armature reaction, the speed of the motor is what? Okay, so let's start from the very beginning. What is the current? As I mentioned earlier, we are having what is called as 100 into 1000 divided by 205 amps. Okay, plus. So this is not the only current that the generator has to produce. It also has to produce the current required by the field. Okay, so that's it. That's as was mentioned earlier, 200 divided by 50, which is equal to 4. Okay, so 504 ampere is what is being produced, though only 500 is delivered into the grid. Okay, so 4 amps is for the for its own purpose, that's for the field. Okay, then now let's talk about the motoring case. Okay, so IL and motoring. Okay, so earlier we called it as IL, now we are talking about the motoring case. Okay, what is that? It takes 10 kilowatt, so 10,000 divided by 200. Okay, and from there, of course, so much of ampere is taken, but then 4 ampere again goes off into the field. Okay, so we are having only 46 amps for the armature sake. Okay, so now we see that EG, okay, earlier was 200 because that was the delivery point. Okay, plus, okay, because it produces more, 504 was the ampere multiplied by 0.025 plus 2. Okay, so this is near around 214.6. Perhaps it's correct. Okay, and this is proportional to the earlier speed, which was same as equal to 300 rpm. Okay, what is the case difference that has happened? Now we are having 200 minus. The change of sign is because now it is a motor. Okay, so 200 is being delivered because the grid remains the same. So 200 volt is being the same because the grid remains the same. So 200 minus 46. Why 46? Because though it had 50 amps, what has happened is that 4 amps is for the sake of the field current. Okay, so the field, okay, it is the field current. So 200 minus 46 into 0.025 minus 2. Again, this also has to be given. That is the brush drop also has to be given, and then we have the remainder as the back EMF. Okay, for the generator case, this is the starting point. EG is going to a starting point. It gives several kinds of drops. Okay, and then it reaches what is called as the grid. Okay, and it also gives current. Okay, 2 types of current. One is the line current and another is the field current. Okay, so in this case, so we see that the voltage has dropped dramatically. That is, the back EMF has become as small as 197. Okay, and that is proportional to the new speed. So now it's very simple. We are having 214 is proportional to 300. So what is 197 proportional to? Okay, so simply cross multiply and you get NS equal to 275.5. Okay, so in this case, I repeat, the answers, the numerical values are important, though you can do some kind of averaging or some kind of approximation. Okay, so now let's move to the 7th problem. 220 volt DC machine supplies 20 amps at 200 volt as a generator. Okay, the armature resistance is 0.2. So what have we noticed so far? We have noticed that there is a 220 volt DC machine which is supplying 20 amps as a generator. So, or in other words, it is supplying 20 into 200 volt so many wattage. Okay, though it is capable of 220 volt DC machine. Okay, so more is produced but less is delivered. Okay, the armature resistance is it's a generator now because it's supplying. Okay, the armature resistance is 0.2 ohms. The machine is operated as motor at the same terminal, but with the terminal voltage 200 volt. Okay, and current, but with the flux increased by 10%. The ratio of the motor speed to generator speed. Okay, so we are having again the same similar kinds of problems. So once you do all of them, you will be very thorough. In fact, machines are supposed to give you more credit in the gate examination. Okay, so what is IL? We saw IL as equal to 20 amps. Okay, and then we also see that EG is equal to 200 plus. Why is EG larger? Because it's a generating voltage. Okay, so 200 plus 20 into 0.2. Okay, so we are having 204, and that is proportional to the earlier speed, which is the earlier speed, and the flux, which is N1 and Phi1. Okay, now we move on to the next case where it is working as a motor. So we calculate EB. How do you calculate EB? Now from 200, that's the terminal voltage, you deduct all the requirements. What are the different requirements? 20 into 0.2. Okay, so you get 196, and this is proportional to N2, the new speed, as also 1.151. Why is 1.151 taken into consideration? Because the flux has increased by 10%. Okay, so now it's simply N2 by N1. You get the ratio as equal to 196 divided by 204. Okay, into 1.1. What is 196? That is the new voltage, and what is 204? The old voltage, and 1.1, that's the flux change. Okay, so you can see that the answer is equal to 0.87. Okay, so of the different answers, it's very clear that 1.06 is not correct. 0.97, 0.96 seem to be too large. So we definitely can, without calculation, we can go for the option A. Okay, so moving on to the last slide, or the last of the questions in this session, we are having a 220 volt DC shunt motor. Okay, which takes 3 amps at no load. Okay, no load is a very interesting condition because at that time it is suffering only the constant losses. Okay, the rotation losses. Okay, so 220 volt DC shunt motor takes 3 amps at no load. It draws 25 amps and running at full load at 1500 rpm. Okay, So both conditions have been differentiated. There's a 220 volt DC shunt motor. That's the capacity of the motor. It takes 3 amps at no load, but it takes 25 amps when running at full load. Okay, and full load speed is equal to 1500 rpm. The armature and shunt resistance are 0.5. Okay, so armature resistance is going to give us the drops, etc. 220 is going to give us the shunt current. Okay, so 220 volt divided by 220. Okay, so 220 was already mentioned as the supply voltage divided by 220 is giving us 1 amps as the field currents lot. Okay, the no load speed in rpm. Okay, so again at no load EB is equal to, okay, it's in both cases we are having a motor. Okay, not unlike in the earlier case where we had a generator and a motor for two problems. Here it's only motor, but there are two cases. One is the no load case and other is the full load case. Okay, so EB for no load case is the same as equal to 220 minus 2 amps. Why is it 2 amps? Because 1 ampere has gone off. Okay, though it takes 3 amps, 1 ampere has gone on to the field, so the rest enters the armature. Okay, so 2 into 0.5. What is 0.5? The armature resistance. So it gives us 219 volt, which is proportional to the no load speed N0 or NO multiplied by 5. Okay, the earlier case 5. Okay. Now we move to the next version when we are having a full load. Okay, so again 200 minus, now it is 24 amps. Why 24 amps? Though it has drawn 25 amps, 1 ampere is going off to the field. So 200 minus 24 to 0.5. Okay, that gives 180, 188, and that's proportional to the full load speed, which is 1500, and 5.1. 5.1 is the same because it's a shunt machine, and in both cases the shunt current remains the same. Okay, so now it's very simple. Again, cross multiplication, etc. So we see that N0 is equal to 290 into 1500 divided by 188, that's equal to 1747.34. Okay, so in this session we generally talked about the EMF. Okay, and in EMF generator. So that's point number 1. 5Z n by 60 into P by A, where 5 is per pole. Okay, Z. So that's the reason why we multiply by P. Okay, then we are having Z as the conductors. Okay, so every turn will have 2 conductors. Okay, and then we are having the speed in RPM. That's the reason why I put 60 on the denominator. And then P is the number of poles, as was mentioned earlier. The number of paths will be given by A. Okay, for a lap wound winding, it will always be P, and for the wave wound, it will always be equal to 2. Okay, so that's it. But that is just EB or EG. Okay, but of course we have to connect it to the terminal voltage. Okay, so terminal voltage is delivery voltage for the generator and supply voltage for the motor. So EG minus IARA will give you V for the generator, but EB V minus IARA will give you EB. Okay, so of course the fields etc. also take their own share of the voltage drop if it's required. Okay, the field obviously will take the current. Okay, so that's important, especially if you are having a shunt field. Remember that the applied voltage is going to, or applied voltage generator voltage is going to be responsible for feeding the shunt field as well. Okay, so we have not discussed series field so far. We'll be going into that in the next session. Okay, so that's over. Now we go to the motors. So in the motors, it's very important to remember that not just these equations, the fact that we are having EBIA being produced such that you can convert it into torque, and the conversion is given by 2 pi nt by 60. Okay, and then the torque and the speed relationship for the series motor is going to be in a hyperbolic sense, and for the shunt motor it's going to be drooping in nature. So this is mostly all that I would like to cover in this session. The next session we'll be going more into speed control, etc. I hope the class has been sort of a complement to whatever you have learned so far, and these are areas where you can score definite marks. Okay, so thank you.